Okay, let's talk about the subject of zero force members. So the basic idea here is that sometimes a structure is loaded in such a way that members within the structure bear no load. So you may have a situation where a particular structural member, again, you may have just loading applied in a certain location where certain members just aren't necessarily needed to bear the load. That the load is spread out then amongst the other members within the structure. But it doesn't mean we shouldn't have those members there. It doesn't mean they're just a waste. It just means that in other loading situations, if the forces are redistributed or applied to different joints, then maybe those members now actually do bear a load. So it doesn't mean, well, I remember when I first took statics, I remember hearing about this and like, well, why would we even put them in there if they're not needed? Well, it's because these structures aren't always going to be subjected to only the loads as they're drawn and presented in a particular problem. They're generic structures, and they could have all kinds of combinations of loads applied to them. So in one situation, they may not be needed, but that doesn't mean in other situations they wouldn't. Two common situations or scenarios where if you see it, you can just write off, say, oh, I don't even have to solve for the force in that one particular member because I know it's zero because it falls into one of these two categories. The first one is if a joint has, and there's a list here, 3 members. So the joint has 3 members, and it has no applied load. And then 2 of the 3 members are collinear. If all 3 of those things are true, the third member bears no load. Let me grab you a couple of examples here. So here's an example. Member member DB right here. So notice at joint B, you have all 3 things. You have joint B has 3 members, there's no applied load, and 2 of the members are collinear. They don't have to be horizontal. That's a common scenario you will encounter, is they'll be horizontal, but in this case, AB is a member, BC is a member, they're collinear, and the third member at this joint B is not in the same line as those, and there's no external load being applied here at joint B. So if you do your sum of forces and in the y direction at joint B, if we draw a free body diagram of joint B, you do the sum of forces in the y direction, the only thing in the y direction is force BD, and there's nothing else. So that sum would then be 0, for example. Right? You see the same thing here on this one. This one here, this would be a 0 force member. There's no external load being applied there. Although So I pointed to this one a second ago. Notice this one looks almost the exact same as that first one I showed you, but notice now at joint B I've got an external load being applied. So now BD is going to have to counteract this external load in the y direction. So now BD is no longer a zero force member, even though those are essentially the same structures. They did put this on a different angle now, but at any rate, just to give you an idea, that's one scenario. It has 3 criteria. But if all 3 of those criteria are met at a particular joint, then then you don't even have to do the math. If you just want to write a state, for me in my class, you could just write a statement that member BD, I think it was, member BD meets the criteria for a zero force member. Just make it clear that you're making that assumption and set BD equal to 0 and go on and solve the rest of the problem without it. That's perfectly fine for me, okay? The second situation, the second scenario where you might encounter, if you see it, then you can say, oh, well, that's a zero force member. If a joint has 2 members, no external loads. By the way, reaction forces count as external loads. So that's an applied force or reaction forces. The only forces at that joint are 2 members. So you have 2 members, no external loads, and the members are not collinear. Then both members bear no load. What do I mean by that? Well, let's say you have this. Some member here, some member vertical. So this is A, B, and C, and something else is attached out here at A and C. Who knows what's out here, but it's something, right? Well, all right, if we do free body diagram of B, notice what you get. You got force AB here, and you got force BC there, and notice the sum of forces in the y direction is equal to 0, which is equal to minus BC, so BC is 0. Notice, and let's say it's angle theta between them, so sum of forces in the x direction, that's not right. I've got BC, I apologize, I've got BC minus AB cosine theta. Okay, so I do have 2 forces in the y direction, but it does hold, what I said earlier does hold true in the x direction, because now I've got minus AB sine theta. Well, as long as I know theta, as long as it's not unknown, if theta can be anything. AB, notice AB has to be 0. And if AB is 0, so this is 0 is equal to BC minus 0, well, that means BC must be 0. They both, if I've got 2 forces, or I'm sorry, 2 members, no external loads, and the members are not collinear. The only way they could be in equilibrium, if there's only 2 of them, is if they're collinear. Then it's possible. Okay. The last thing I want to talk a little bit about is the idea of space trusses. Space trusses. These are 3D trusses. Now, for me, when I teach a statics class, I think this is, it's perfectly okay to go through it. I'm not gonna assign any space truss homeworks. That's just me. I'm not gonna put it on any exams. I'm just gonna mention it's a thing that we talk about in chapter 6. They're really cool. They're a lot of math. And I think there's just other things that we can do in 3 dimensions that seem a little more realistic to me. I mean, I'm not saying you won't ever encounter a 3-dimensional truss, but most trusses we encounter would be, you can treat it as a 2-dimensional entity. But there are some trusses that would be 3-dimensional in nature. And the biggest thing to mention here is these can be modeled as having ball and socket joints instead of pins. Remember our friend here, the ball and socket joint. This is something that you can rotate about an x-axis, about a y-axis, and you can spin it in the z-axis. So rotation's allowed in all directions, but you can't move it in the x, the y, or the z direction. So it's allowed to rotate in any direction, but it's not allowed to move in any direction. So a reaction force in all 3 directions. But because it's a truss, forces only applied at the joints, just like we see in a 2-dimensional truss. This causes each force is a 2-force member. So you have either tension or compression directed along the axis of the member, and just then attached at ball and socket joints. So instead of having an X, Y, and Z component, you know the direction of force. It's just simply in the direction of the members that are attached at the joints. So it works just like a 2D truss. That's really about all I would normally spend in a class. Again, just at the sophomore level for engineers, it's not too hard necessarily to ask you to analyze a 3-dimensional truss. I just find it's a little more tedious, and we've got way too much to do in a statics class as it is, especially at a community college like us, where we're trying to satisfy transfer agreements between 4 different ABET accredited engineering programs in the area. I've just got too much to do, so I normally don't do too much more than just simply say that right there, maybe show you some pictures out of the book, and call that done. All right, I'm going to stop here. We'll do an example problem on the next video.